Okay. Yes, and sorry for the delay. It seems that I have this network problem at Helsinki library. So, yeah, as Mr. Imam already introduced, my name is Arif. I got my PhD from Aalto, and it's my pleasure for me to have this sharing for both of my universities, for Aalto and for ITB. So basically, I am a hydrometallurgist. I will just carry on with the slides. Yeah, this is a little bit of my profile. I was working in PT Antam as metallurgist, and I was in the only Indonesian precious metal refinery, which is called UBPP Logam Mulia. Uh, I was project engineer there, and also doing project for copper smelter and silver electrorefining modernization. Both projects connected me with Finland through Metso Autotech company. So I know more about Finnish technology from those two projects. And I pursue my higher education at Aalto University, as mentioned. Uh, I was doctoral researcher in system integrated mineral processing. So in Alto, I had this privilege joining a lot of projects. I only put the related project for this kind our topic today. So in this system integrated mineral processing project or SIM project at that moment, it is called SIM project. We built this kind of tools of modeling for industrial processes. For me, I deal a lot with silver and copper electrorefining with my colleague Taina Kaliomaki and Mimiko Kiviloma. And after finishing my doctoral researcher, after I'm being a doctor here in Alto, I did this postdoctoral researcher in focus for process modeling. In the second modeling that I did, this process modeling as postdoc, I use COMSOL multiphysics software. So it's kind of a new thing for me, but I learned a lot from there. So that's a little bit of my background. And without further ado, in this section or in today's discussion, I will share you my knowledge both from the industrial practices and from academic research in this 2 hours opportunity. Maybe I couldn't really touch everything, but I will try my best to give you insight of what is precious metal refinery. So in the first section, I will introduce you in the industrial practice, and in the second sections we will try to understand the process behind the electrochemistry that happening in the metal refining. So precious metal refining industrial overview. What is it? This precious metal refining. So if we imagine a mining company, mining company they why mining companies they make concentrate, for example, copper concentrates, or in this precious metals case is a dore bullion. It's called dore bullion. Why? Because in mining company, it's not a good option to have refineries or smelter on site due to a lot of reasons. One of it is like mineable resource is a non-renewable. So at some point, the mining resource will be depleted. So why we build these smelter facilities in a location that could be a remote location, could be hard to reach, and then when the resource is depleted, so the facility cannot be used anymore. So it will be a waste. Second one, the cut-off grade. Sorry, the cut-off grade of gold. It's now in today's price about $1,800 per troy ounce. It's at about zero point 0.5 to 1 grams per ton. So the amount of gold mined there is not a lot. Well, for we can make exclusion for big companies who mines tons and tons of gold every day. But what about the small gold mining companies? It's not really feasible for them to make a smelter or metal refiner there. So with all of these reasons and also access to customer and bullion banks, because precious metal refinery is metallurgical site that really connects with the customer. I mean, by the customer now here is like a retail customer. For example, if we talk about copper smelters, they produce copper cathodes, so it's not really in touch with retail customer. But for precious metal refinery, they have close relation with customer, trading these gold bullions as a media for investment. So in take into account of all the facts that we have in previous slides, we can really separate the activities, the integrated activities of producing pure precious metals by two main activities. One is mining and extraction, showed by the dotted box, and then the other activities is refining, fabrication, and recycling, showed by this the box on the right side. These two activities can be integrated, owned by the same company. For example, in Indonesia, Antam has been practicing this integrated combined process of gold mining and gold refining. In Finland, there is this Boliden also practicing both activities as integrated company, but not a lot of companies doing that in the world. So in that sense, precious metal refining. So I will abbreviate this with PMR because that is the common term. Is industrial unit for refining gold bearing materials. We will in touch with we will how to say briefly touch this gold bearing material. What kind of gold bearing material is it that can be refined there? So, and PMR can be integrated. I've already informed this before. And the final product of PMR, precious metal refinery, such as gold bars, silver granules, and other product as gold granules, silver nitrate, and any other kind of gold alloys. So in order to have the same perceptions all over the world of what is the sellable or what is the marketable final product of a PMR, there is this association called London Bullion Market Association, or LBMA, comprises of gold bullion banks, assayers, or laboratories, mining industries, and something, and everyone else that involved in this chain of business. So they put some kind of regulation of, for example, for a marketable pure gold should contain not less than 99.99% of gold. So that is like the minimum content of a gold bar. And for silver, pure silver, it cannot be less than 99.5% of silver. So yeah, those kind of regulations take place for this business. In this schematic PMR business process, these two process of mining and then precious metal refining, you can see there is this. Sorry, I will put my pointer on. Yeah, so you can see this straight line as the material flow, and then this dash line as the what is it? As the accounting flow or on the cash flow. So mining companies, they can send Dore bullion and also some scraps containing gold to a precious metal refinery, and then they refine it, and then they send back the pure gold and silver at a agreed recovery. And then this is the cash flow. So the mining companies, they will pay for TC and RC, so, or this is like treatment charge and refining charge. And also precious metal refinery can charge for a penalty. Can pay for penalty if they fail to refine the material at an agreed recovery and time. So in this sense, even though in this metallurgical process we are dealing with high valued materials such as gold, silver, and even PGMs, platinum, palladium, and so on, we cannot really, how to say, we cannot really take this process lightly because the material can be owned by other companies, and we only in the precious metal refining can only receive TCRC as their income, so they need to do this process efficiently. And then, yes, this is a little bit in touch with the gold bearing materials. So for the gold bearing materials, mainly precious metal refinery process this doré bullion, which is produced by gold mining, and then also they receive this jewelry scrap, anode slimes. So the slimes from copper electrorefining, it also contain a high amount of gold, can be 3 to 5% or even higher, depends on the copper concentrate, and slugs or precipitates of industrial waste that contains precious metals. So these kind of materials can be processed in a precious metal refinery. You can see this like a jewelry scrap. I receive a lot of this jewelry scrap when I was working in PT Antam. So we also process this kind of things, but mainly it's like doré from mining company. This is a processing route that I modified from a practice in Ren Refinery, South Africa. Ren Refinery is like the biggest and I would say, in the most modern facility for precious metal refinery. So the doré bullion, crude doré bullion, usually contain silver. Usually the combined content of silver and gold is more than 90%. It's smelted and some samples are taken there. And if the materials has this high gold content, they will go through this high gold bullion process route. And if they have like lower gold content, they will go to the silver refining process route. Because mainly it's like the gold and silver there, they have like 90% content. So which one that we need to refine first? So it's just a matter of economical value and also a speed of processing. And then for the high gold bullion, it will go to chlorination. As I mentioned it again, this is a practice in Ren refinery. Not all the precious metal refinery they have this kind of facilities. And for chlorinations, after chlorinations, they will produce gold anodes. So the other material except gold, so all the impurities, they will form chlorides, which will precipitate, and then it will go to silver leach. So the silver chlorides in this material is reduced into silver metals, and then it will go to silver electrorefining. But for the gold, it will go directly to gold electrorefining and to produce a 99.99% of gold. Yeah, I took this from my doctoral dissertation. So sorry. So we will go through the smelting and then all of this process altogether in details. So smelting process is, as the earlier slide informed, it's the first process that that this bullion goes through. The smelting of the bullion is conducted in gas or oil furnaces. So this is the example of caldo furnace. This is the only free rights that can a picture that I can find in the internet. It seems that it is in French. So in this caldo furnace, the metal is like smelted there, and then some oxygen is blown through this lens, and then some additional fluxes goes through the metals also, in order to oxidize all the impurities and to make more refined materials for the process. The objective of this smelting process is to increase gold content and to take representative samples. So if you go to any precious metal refineries, this is the only process that you can visit directly, because all the process is like how to say restricted. So in the smelting process, the mining company's representative, which is mostly a lab or a sayer, they will They will take part in the process, and then they will take some samples to make an agreement with the precious metal refinery. Oh, okay, so this is the content of our sample. So as agreed term, we will receive this much amount of gold and silver in certain period of process. So there, the witnessing process is also taken place. In the metallurgical view, oxygen and fluxes are introduced in the process and to oxidize all the impurities, mainly base metals. And the common fluxes that are used, they are like borax or sodium borax, this chemical formula. The borax it lowers the fusion point of the metal oxide. I think Professor Taskinen and Dr. Imam knows better this than me. And then also sodium carbonate for the desulfuring and oxidizing agent, and also potassium nitrate for powerful oxidizing agent. But bear in mind that the potassium nitrate use is quite, how to say, quite cautiously. Like it's quite dangerous thing. And then after this melting and the gold content increases, so it will go through the gold roots if it has high amount of gold. And in the gold roots, not all of the precious metal refinery adopt one process. They most of the time they have like several different options, and then so there are two main routes of gold refining. After the feedstock or the bullion is refined in the smelting process, it will go to this. In the first, I will talk one by one. In the first route, it will go to another pre-refining where the material is like melted again and some oxidant added. So mainly here is like a chlorine gas. So chlorine gas, they will further make a chlorides out of all the material except gold. Mainly the target here is mainly silver. So to take away silver from the bullion. So when the gold has this higher 90% higher purity, it will go to electrorefining, and usually they use aqua regia as medium there to produce precious metals, 99.99% of gold. Another route is that the the bullion is dissolved by adding aqua regia with some oxidant, and then the how to say, the gold is leached there, and then it precipitate with some reductant, for example, SO2 gas or some kind of cementation process to produce gold or 99% of precious metal. In this flow sheet, the pre-refining process mainly called Miller process. So Miller is like dry chlorination process, and the electrorefining is called Wohlwill process. Miller Wohlwill process on this left side of root is actually more robust process compared to the right side because it has higher kinetics of process, smelting and then adding chlorine gas and then electrorefining. And also on the right side on the right process, it has some kind of difficulties to process bullion that has more than 15% of silver. We will go through with this in few slides. So it this one has higher kinetic, and this one has this limitation of processing a certain content of bullion. So for me, it's no brainer. I think the left side of root is better than it's the best of out of these two. A little bit about Miller process. So Dore bullion, once it's melted and then added with chlorine gas, this is some kind of a melting point and gives free energy of selected metal chlorides that is usually exists in the gold bullion. As we can see from the Gibbs energy, that all of the materials except gold, they will form these chlorides. So gold will be safe there in the metal melts, but all the chlorides will form slags, which is further processed to recover the silver. So by time, this chart shows the reduction or the decrease of content for all impurities by time of this chlorination process. As we can see, the amount of iron in the bullion drastically decrease in firstly, and then zinc, lead, copper, and the last thing is silver. So chlorination times usually took like about 1 hour process to remove all of these metals from the bullion to make at least 99.5% of gold in the bullion. Once the gold bullion reaches 99.5%, it will go through this wall wheel cell or an electrorefining cell. Electrorefining cell mainly comprised of three main elements, which is a cathode, anode, and electrolyte. So in this gold electrorefining, the gold will dissolve from anode. So the anode is the impure gold, so 99.5, and then the gold will dissolve and then will be deposited onto this titanium cathode. So this is in these pictures, it's a hydrochloric based electrolyte, but mainly people use aqua regia. And then also in the cell, we introduce air bubble for agitation. So to mix the electrolyte to have a steady and homogeneous electrolyte all the time during the process. So will mainly firstly developed by Norddeutsche Refinery in Hamburg. Now it's called Aurubis. I have visited Aurubis here back in 2016 with Pekka, if I'm not mistaken. And yeah, so this is the process information I already mentioned earlier. So gold dissolved from anodes and then deposit in cathode. Undissolved impurities will be accumulated at the bottom of the cells. As you guys maybe still remember from previous slides, that silver chloride will form lastly in the chlorination process. So mainly this slime content is like silver chlorides there. And yeah, and sometimes it's like titanium or sorry, not titanium, platinum and some undissolved gold. Yes. And wait a second. So to get that all information settled, I have a little bit of quiz here. So for a refinery with an installed gold process of dissolution and precipitation, so let's imagine a refinery, they don't have this Miller and Wohlwill process. So they will go with the right side of process. How should they treat this 15% with bullion that has the silver content of more than 15%? So
I will give
you
chocolate.
guys might.
Who can answer this? I will bring the
All
chocolate.
right.
Yeah, Mas Arif, because I give chocolate if there is
Yeah.
question. I give chocolate to one who answer.
Okay. Yeah. So just to refresh our memory, I will show the slides. So just pretend a facility they don't have this one. So they only have the right side of the root dissolution and precipitation using aqua regia. So what will happen if they receive this kind of material from jewelry scrap or gold mining companies? How do they treat it? So you can submit your answer to Imam, but I will proceed in
No, they can
10
answer
seconds.
directly here, Pak Arif.
Oh, okay. Okay. All
Okay.
right. Yeah, yeah. So you guys can freely answer. There is no correct answer
Yes.
here. Just like what do you think?
Yes. We appreciate the brave of you.
Yeah. So bear in mind using aqua regia to dissolve this bullion. Aqua regia, as we know, it has nitric acid content and also hydrochloric acid content. So silver cannot be dissolved because it has this chlorine ions. So silver will form silver chlorides. So this material is like hardly to dissolve 15% of silver. So hello, is there anyone that brave enough to answer this simple question? All right. If not, then I can answer it, and Imam can give that chocolate to me. So,
Yes, I will come to you. Okay.
so the answer is like this. As we know, the solution of bouillon with high silver using aqua regia is like hard, very hard, because silver chloride is not dissolved there, and it precipitates, which hinder further dissolution. So there are some kind of option, Most common treatment. So this is the industrial practice for this high silver dissolution is like they add low silver material or even base metal, for example, copper scraps or silver scraps that they have from their process. So unused or unprocessed silver, they put it into this bullion to decrease the silver content. So the silver surface on the metal will not be hinder the dissolution of gold. And the second one is pre-treat the material with nitric acid. As we know, silver is very, very soluble in nitric acid. It's easily dissolved in nitric acid. So they will use nitric acid to dissolve silver away from the material, and the gold will stay there because gold cannot really dissolve in the nitric acid without any complexing agent. So silver content will decrease quite a lot, and then they will treat the remaining metals to this aqua regia dissolution. And the third one, this is if they don't want to, how to say, adapt or don't want to be creative with the circumstances. So they will just carry on with the gold dissolutions until a point of passivation. So this material will be casted into granules, and then it will be put into this, how to say, digesting cell or leaching cell, and then put aqua regia there. And they will do that until the granules cannot be is not dissolved again, so until it really pacificates, and then they will filter it. So this kind of three options are can be done for those refinery that don't have this Wohlwill Miller process. All right, that is for gold. And then I will carry on with, oh, this is another, sorry, gold refining parameters. So yeah, after gold is like how to say, in the gold refining electrorefining process, we can see these are the parameters that is applied in the process. We can see here I have my source like 70 years ago, a book written by this Mantel in 1940s. So there are five examples from Mantel, and they use this kind of processing parameters. And I got this general Wohlwill cell from a publication by Moiman and Simpson in 2016. So it's like it's like half a decade distance between these two, and even more. But as we can see here, the operating parameters they are look similar. So for example, this Norddeutsche Avinary in Arubi Hamburg and American is this is typo. They use this kind of electrolyte with this kind of temperature. And at the moment in 2016, General Wohlwill cell practices. So they use this kind of range, which is a little bit similar. So there's not a lot of changes in this particular field of processing. Next, we will go to silver roots. So for a high silver bullion, of course, we cannot we cannot process it through the gold process first, because gold is like only minor there. Even though for us, we really want to get the gold out first, because it's like the most precious metal there, the highest value in this Dure bullion. So in a PMR or in a precious metal refinery, if they can get if they can refine gold as fast as they can,
Yes.
that is like really really beneficial for them. Because for example, if they can refine gold in 3 days, and then they need to return this gold to the mining companies in 7 days, so they have this 4 days of window, which they can use it for bullion tradings, this investment trading, this kind of thing. So it's huge advantages. So if they can choose, they will choose gold route first. But then for high silver bullion, they cannot really do that. They cannot really do that. So for the high silver bullion, unfortunately, it will need to go to silver routes. I have also two options here in
Nice.
silver routes for very high.
Nice. Nice.
Sorry, for high silver bullion, the first route is like anode casting,
Nice.
and
Nice.
this bullion will be casted into silver anodes, and these anodes will be processed through electrorefining. And in this electrorefining, it will produce fine silver, minimum 99.5%, as I mentioned, regulated by LBMA, and also anode slimes. As we can see, it goes to one, two process to produce gold. And usually, this electrorefining process takes 3 to 5 days. So the gold will be like in close to the deadline for shipment to the gold mining company. So this is unpreferable, but the most robust process. And the other option is that we can process this high silver during bullion through parting. So the silver bullion is leached or dissolved in a nitric acid solution. The silver will be dissolved, and then it will stay in the electrolyte as silver electrolyte, silver nitrate electrolyte. But the gold will stay on the solid material as a gold residue. As we can see here, it's only like one process, and we will get the gold. So after that, we can process the silver electrolyte through electrowinning, and we don't really have time limitation in this kind of process since we already take out the most valuable metal first. So the left side of the process is the most robust, but it's unfavorable. The right side is not so much robust process because in electrowinning, uh, it consumes higher energy compared to electrorefining. But then these are the options that are available. In silver electrorefining, similar to gold, it has this impure silver as anode. So silver will dissolve from anode and then goes through cathode. So mostly it's similar. The electrolyte, the differences are like one. The electrolyte here, it's not aqua regia, it's silver nitrate electrolyte. So AgNO3, silver nitrate electrolyte with some kind of free acid content here. And the second difference is that the 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 material that how to say accumulate at the bottom is not anode slimes, but it's the final product. So this is the silver crystals. It happens because silver is not solidly deposited onto cathode. For copper, if you guys have visited a copper smelter, in copper, the deposition of copper on cathode is like solid deposition. So the copper will stay there and cathodically protected from the process. Gold also behave the same. Gold will solidly deposited on cathode surface, but silver is different. The deposition of silver is not in solid deposition, but it's a dendritic deposition. So by time silver, because it's not solid, it will fall down to the bottom of the cells, and it's not cathodically protected. So silver here can be redissolved into the electrolyte again because of the free acid content here. That's why the free acid in silver electrolyte, it's how to say, is quite limited at low point, maximum 10 grams per liter. While in gold, it can be 100 grams per liter, the free acid. So that is one. And sorry, and the slime, the impure, the silver slime will be collected inside this anode bag. So for silver electrorefining, the anode will be put into this anode bag. It's a porous bag made from nylon. Uh, so the silver can dissolve and goes through this bag, but then the gold and other material will be deposited inside this anode pack. That's why in this process, the anode pack needs to be taken care periodically to have an efficient process. This is the industrial silver electrorefining from the same source. It's very good book if you want to learn precious metal refinery. It's a Mantel from 1940. So these are the parameters for both Mobius and Balpactum cell. If I forgot to mention earlier, Mobius cell is the cell schematic that we saw earlier in previous slide. But Balpactum cell is like different. Balpactum cell, so Mobius cell arrangement is like this vertically, but Balpactum cells arrangement is like horizontally. So those are the main difference. For me, Mobius cell is much more efficient because we can see from this Mantel data, I put into perspective with these calculated values of this anode area and anode area per cell. So in Mobius cell, the area that covered by electrolyte is higher than in Balpactum cell. So in short, in Mobius cell, we need less electrolyte than Balpactum cell, or we can put more anode to be processed than Balpactum cell because it has like twice of the area. So for me, it's very easy option. Mobius cell for me is like the most robust among these two. And this electrorefining process, as you can see, the silver content is like 30, 60 for me. This is very low. And then this free acid content is like some refinery have like none, 0. And some has like 1 grams per liter, and then 1, 2. So the amount of free nitric acid there is like kept low because it can dissolve again the pure product of the process. It runs in current density of 300 to 400 amps and sometimes like 600. But my dissertation proves that we can go up to 1,000 without any problem. But we can check it later on. And then this is to compare with Mantel. This is the industrial silver electrorefining, which I compiled from different sources. So I put this table in my dissertation. So from Leh in 1973 to the latest dissertation by Maurel Lopez at Aachen, at WTH Aachen, 2017, the electrolyte profile is looks like this. It doesn't really differ much. It doesn't really differ much. This paper by Maliarik is very interesting. So Maliarik works for Autotech at that time. I think he still works for Autotech. So he published this paper, which which promotes this high current density process by Autotech. So in this publication by Maliarik, he suggests that the current density can go very, very high. So also does Kramer, but in Maliarik, it's like really, really motivating to go to higher current density in that process. And it has like very low energy consumption and so on. So yeah, this is one paper that also motivates me in investigate further about this process. And next, so after we go through silver process, another quiz to put those knowledge into applications. So you guys, I hope you guys will remember this course, and yeah, I will share these slides, of course. So for a PMR, which have both option of electrowinning and electrorefining, electrorefining is like the silver casted into silver anodes and then processed through electrorefining. And electrowinning is like the silver bullion is dissolved first and then put into electrowinning. So which is the best case for these two types of bullion? The first bullion has the silver content of 80 to 95, and the second one has this silver content of lower and higher gold content. So I will give 1 minute to wait if somebody wants to raise hands and say some opinions about this, please? Or Imam or Danes, do you want to answer? Hello? I got somebody.
Okay, Danes maybe.
Okay. Good afternoon,
Guys,
Pak
please.
Arif.
Yes.
I would like to answer maybe for the first bullion. I think the better route for it is through the electrorefining process because it has high enough silver content and so
Yeah.
gold.
Yes. Yeah, that's correct. So you have the right
Okay,
for
I
a
will give you
chocolate
chocolate,
bar.
Danes. How many chocolate you got already? 1 kilo? 2 kilo? Okay.
Yeah. So the answer is like for the first bullion, yes, that's correct. The first bullion, it's better to go through electrorefining since the gold stock is like very low, and we are not in haste to recover gold as fast as we can. And from the process perspective, anode passivation can also be minimized because gold cannot be dissolved in in nitric acid. So when gold exists in the silver anodes, it will passivate the anode surface. So the process can be passivated quite severely. But with this amount of gold, less than 20%, it's not a really huge problem. But for the second one, yes, true. Yes, that is true. We can electrowinning also. But of course, there are another option. So this is the how to say the creativity. If we work in industry, we need to take a fast solutions. So in my previous experience in Antam, we smelt this high gold bullion added with silver scraps and then put it into electrorefining because we much prefer to use the electrorefining cells as it operates at lower voltage and has this lower energy consumption and so on. So yeah, but there are some kind of option to deal with this kind of materials. All right. So that was the industrial perspective for gold and silver refining. And now I will go to the electrorefining itself, the electrochemistry process of refining gold and silver. Of course, I cannot really cover the whole concept of electrorefining in presentation, probably like in half an hour. But I will try my best to make you guys understand what is the system. So yeah, so general process is like this. We have this box of electrochemistry cell. We call it electrochemistry cell. This is the schematic of the cell. So we have these electrodes. The positive charge electrode will act as cathode, and the negative charge electrode will act as anode. So from this different charge, positive and negative, there will be some kind of reduction oxidation process. So in the anode, it will be like oxidation process, and in cathode it will be a reduction process. For example, in silver case, silver will be oxidized in anode from the impure silver anode. So silver will be oxidized into silver +1, and at the cathode, silver will be deposited from silver +1 into silver. So that is the thing, and there are some variables, of course, that takes into effect to the process. For example, electrode variables is like the materials. In this case, if we have like impurities, surface area, geometry, and surface condition. So by what it means by geometry is like usually people have this slab of an electrode for this precious metal refinery. But then another practice can also this material can also be granules. So these granules will be fed continuously into this titanium anode box. So the silver will be dissolved, and then how to say the granule will be fed like continuously. So granule goes in, dissolve, and then another granule goes in, so it can be like continuous silver electrorefining process. So that is by means by geometry. And then another in the process wise and solution. So the transfer of the silver. So when silver dissolve from anode goes to cathode, there are a lot of barriers that it goes through. Is it controlled by diffusion? Is it controlled by convection, or is it controlled by something else? So that is also another important parameters. And another one is solution variables. As we know that we put electricity into work here. So electricity requires a medium that is conductive for it to travel across. And as we know, pure water is like not conductive enough. But then if we have silver nitrate there in the solution and we have free acid in the solution, they will increase conductivity. They will increase conductivity of solution. So solution variables in this process is very, very important. Very, very important. In fact, when I did my dissertation, that was the first area that I measured is the silver conductivity from the process. And then, so I already mentioned this, half cell of oxidation occurs on anode surface, another half on cathode surface. Electrolyte connect both anode and cathode and supply the ions for deposition process. So the other role of electrolyte, except especially besides it needs to conduct the electricity. It also needs to have these materials that can dissolve the metal from anode, and also that has the ions that needs to be deposited on the cathode. So that is also the other role of electrolyte. So if you want to refine silver, for example, then the electrolyte will need to have silver in the solutions. It's like the electrolyte need to have silver nitrate. The nitrate ions will dissolve silver, and the silver ions will deposit it on the cathode. So that's how it goes. So this is what happened with the process or transfer of silver from the bulk, from the solutions into the surface of the electrode. Surface can be anode, or can be act as anode or cathode, but this is the main schematic that happens there. So from the bulk, it will goes through this electrode surface region. So the region close to the electrode here, for example, in gold refining, it's like a gold chloride complex from the bulk will travels to the close surface, to the region close to the electrode surface, and then the gold ions will will separate from the complex, and then absorb to the surface and then reduce here as pure gold, or vice versa. The gold, if it acts as anode, will dissolve as gold plus 3 or gold plus 1. Gold plus 1 is undesirable. Uh, so people, this is one reason why for gold refining it has high free acid content, because to avoid the formation of gold plus 1, so it needs to be very, very oxidative. So the gold will be how to say oxidized there into gold plus 3, and then it will form complex with the chloride, and then it will goes to the bulk again. So there are a lot of process that's going on for a simple oxidation and reduction process in the electrorefining. I took this picture from a book written by Bart and Faulkner. For me personally, this book is the best ever book for studying electrochemistry. So I highly suggest you to read this book. It's very easy to understand there. And then another brief of electrolysis system. So Michael Faraday, I took this picture. Michael Faraday discovered that to react a mole of electron, it requires approximately 96,500 coulombs of charge. So from that alone, for example, if we have this kind of reaction, if we have n mole of metals with Z valence, with Z oxidation value, of course, we requires n times z of electrons in perspective of electroneutrality to produce pure metals. In that sense, the total charge that we require, so total charge is like a total current that we introduce a system in a certain period. So if you guys, how to say, for example, in the mobile power banks, it has this ampere hour or milliampere hour. It's like the charge of that power banks. So the total charge from this chemical reaction perspective is equal to Nz, n times z, then total number of moles of electron required for the process, times the F, which is a constant of Faraday. The value that Faraday discovered to move 1 mole of electron. So the amount of mole of electron times the Faraday constant. From this discovery alone, so if we think that this electrorefining is like, yes, it's only electricity that does the job there. So when electricity is the main work in a system, so we call work is like W, right? The how to say the symbol. The work is like equal to potentials times the total charge there. And as we know that the total charge can be replaced by this chemical parameters of moles, electrode valence, and Faraday constants. So we can, at a constant temperature and pressure, the Gibbs free energy, which is mainly contributed by the electricity work, will be like this. Will be E times the amount of mole and then Faraday constant. So in that sense, we can derive the Gibbs free energy like this. How to say, the correlation of Gibbs free energy to the electrical energy like this. And then that is like from the potential dynamic sorry, for the thermodynamic perspective. But what about the productivity of the process? How can we calculate the productivity of the process? So based on this Faraday constant, so based on this equation alone, we can rearrange the equation so we can calculate the amount of moles, the amount of moles that is produced in a certain period by introducing certain amount of current. And then if we want to calculate the mass that is produced there, we can also put into perspective that a mole is like mass divided by molecular mass of that related substance. So this is the very, very common equation that people use in electrorefining. So if you, for a process with this current that flows there in 3 days, for example, if we do silver electrorefining, okay, I have this current for 3 days. So will I have enough silver anodes to be put there? I mean, what if the silver anodes depleted, like gone in just 1 day because we put too much current there? So we can calculate it from this equation easily, and this is very, very, very friendly to use. So while current does the job in electrorefining, industry pay for the total energy that is consumed, which is the cell voltage that is related there. So effect of potential to current density cannot be calculated theoretically. What I mean by this statement is that if you remember the flow of the materials in from the bulk to electrode surface there, it has a lot of how to say, a lot of parts that this is chemically reaction control, this is mass diffusion, this is convection control. So a lot of controls, like very complex mechanism happening there. So if we cannot really calculate, like if I put this potential, I will get this current density and so on. So it's not as easy as that, unfortunately. So it must be measured by electrochemical techniques. One, for example, is a polarization curve. So I tried to how to say, to illustrate this process like this. This is my drawing. As we can see, drawing even a figure is not my best suit. So, for example, this is the the result, if we measure a sample with polarization curve. So usually we measure from the cathodic side and then goes to the exchange, how to say, current density or the OCP potential, and then we goes up again to the anodic side. So this form of chart, you can see this kind of form of chart if you use European technique of drawing polarization curve. But for American standard, usually they have potential as the y-axis and log of current as x-axis. So it will goes like this. So this is the European way of drawing this polarization curve. So if we want to put a certain current density for this process, then of course we will have this over potential of anode here. So this point is like our direction here. We need to go there. So from the open circuit potential, we need to introduce this much amount of polarization for each of the electrodes. So that is for a surface that can act both as anode and cathode. But as we know, in electrorefining, anode and cathode, they are two different surfaces, two different materials. And then they are separated by electrolyte. These are separated by electrolyte. So once the current goes through the electrolyte, there will be something called IR drop. IR drop, this is the total voltage that is resulted from this process. So if we how to say, flow a certain current here with the resistivity of the electrolyte, it will impact this IR drop as additional potential to the cell voltage. So from this illustration, from this simplistic illustration, the total cell potential for this electrorefining cell or any electrochemistry cell, the total cell potential is like the over potential of cathode plus the IR drop, and then plus the over potential of anode. And from what I measured, from what I read from publications and what I measured in the lab, IR drop is actually quite significant because cathode and anode is like very conductive, especially if we talk about silver. Silver is the most conductive materials that ever exist, even better than what is it, copper or gold. So only lost to graphene, if I'm not mistaken. So air drop is very significant. It can be like 55 to 80% of total cell voltage. So basically, an industry, they can pay 80% of their energy for something that is like not in the process itself. It's just a medium, cost of the medium. So to have low air drop, high conductivity of electrolyte is required, of course. And as we can see here, with the known cell potential, we can calculate the energy on the work that needs to be done in the process with cell potential E times the total charge, I times T. So, oh my God, I forgot to hide the answer. So I have this another quiz, like derive Nernst equation from equation on slide 24. So I rewrite this equation in slide 24 that delta G, the Gibbs free energy with the potential energy of electrochemistry process is like this. So if we have the initial Gibbs free energy, Gibbs free energy is like this. So we from the first equation we can tell that the standard Gibbs energy relation to the standard potential is like can be shown by equation 3. So by combining the equation 1 and 3 to equation 2, or substitute the value of delta G to here, and then substitute the delta G0 to here, so we can have this kind of equations. It's the Nernst equations. So this Nernst equation can be very, very handy For example, if we want to know the effect of temperature, the effect of concentrations in the solutions to the potential or reduction potentials of the metals that we want to process there in the process. So I want to talk a little bit about current efficiency and energy consumption. So in the industrial term, current efficiency is calculated by making a ratio from the real deposit mass. So if we process silver electrorefining, for example, from theoretical Faraday equation, okay, we should have 1 tons or 100 kilograms of silver deposited by 1 day, for example. But then in the real process, we only have like 95 or 98 or 99. That is the ratio of both values is the current efficiency. So of course, current is only used for dissolving silver on anode and depositing silver on cathode. But then there are many things that can use up this current. For example, deposition of unwanted materials or dissolution of unwanted materials. For example, if in the silver anode it has copper content or lead, copper or lead content, like copper and lead can be dissolved in silver and in nitric acid. So a fraction of current can also be used to dissolve copper and lead into electrolyte, and a fraction of current can also be used to deposit those impurities on cathode. So in a sense, if we want to have high current efficiency, of course, we need to limit this fraction of current that is used for any other things. So some factors that reducing current efficiency are like stray current or bad connection in bus bar in the process, impurities deposition and also redissolution of products. So I have touched this impurities deposition. So if we use that fraction of current to deposit copper, then also reduce the current efficiency. In case of silver electrorefining, redissolution of product is very, how to say, severely affected the current efficiency. So as we know that in silver process, silver is like accumulated on the bottom of the cell. And since the electrolyte has nitric acid, it will dissolve the fine product silver. In energy consumption in the process, usually we have this unit of kilowatt hour per kilogram, and then it's known as specific energy consumption. So we can easily put that into perspective. Okay, kilowatt hour is like the work that needs to be done, and then the kilogram is the mass that produced by that work. So this is the specific energy consumptions of electrorefining process. Of course, specific energy consumption needs to go as low as we can in this sense. This is a little bit about current efficiency. So this is if I'm not mistaken, the first or the second paper that I published. So I studied the effect of this electrolyte condition of silver ions or silver content in electrolyte, nitric acid, and temperature to the silver electrorefining. And as we can see here, I put different over potentials in this process from 150 to 200 millivolts and different temperatures and concentration of acid and also concentration of silver there. And it produces a quite interesting current efficiency. So as we can see here, with the increase of nitric acid, the current efficiency just drop. Like, I mean, if how to say, from 87% shown by this ISO efficiency dash line to 85%. And increase of silver content actually also decrease the current efficiency. So it's quite interesting. But that is the results that I got from the measurements. So in this sense, to have very high current efficiency, we need to reduce the nitric acid content, and also it's safer to reduce also the uh, silver ion content. Why this is happening? Because there is this special, how to say, special mechanism that happening for silver dissolution in nitric acid medium. So the content of nitrate NO3 ions, NO3 minus ions there, it will it has this self-catalytic phenomenon. So the ions from both the free acid and the ions from this silver nitrate to make this electrolyte, it has this autocatalytic process to dissolve the pure silver at the bottom of the cells. That's why the the concentration of both nitric acid and silver needs to be limited as low as possible from these findings. Next. So one thing, if how to say, to improve an electrorefining process, is that we need to have a clear map of what is the interact, how to say, what is the interrelated effect if we change or if we alter one parameters to other. So if we have, as we know, we have this anode, electrolyte, and cathode. That is as three main components in electrorefining process. Anode has this impurity, electrolyte has concentrations, temperature, and conductivity. So altering this impurity content or limiting the impurities or increasing concentrations of temperature, it has very various effects of each other. For example, for impurity, if I have non-noble impurities, for example, copper or lead, copper can be dissolved into electrolyte during silver electrorefining process. So first, it will contaminate the electrolyte. And second, because the concentrations of electrolyte change, it will change the concentration of the electrolyte. So it's not only silver there, but we also have copper. So by having other impurities in electrolyte, it will also change the conductivity, and it will also contaminate the product that we can get from the process. So product contaminations happens in this cathode, and it will reduce the product purity. But for conductivity, it can how to say, it can affect, not necessarily increase, but it can affect the specific energy consumption there. So it has this complicated relation effect if we want to improve this electrorefining process. So we need to make a map, like what will happen if we change one process to another. So that's. But then after all of that, after we discussing about data from Mantel book in 1940, which has like similar to Neumann and Simpsons in 2016. So actually, there is no is there any notable improvement in the electrorefining process? If the process from 70 years ago, it's still the same with the one that we have now. So I put some of these notable, I would say, breakthrough or some significant survey or publications by several authors here. So here I put the values based on the correlation of silver concentrations and current density. As we can see here, the research, uh, how to say, from years to years to years, it goes to higher, and higher current density. And the notable paper that I mentioned earlier is by Maliarik from Autotech, where they started to commercialize the high current density process. And the correlation is that for higher current density process, it seems from these publications, it seems it has higher correlations of having higher silver concentrations in the solution. So this is what intrigued me also to study further of this high current density silver electrorefining. So to put into perspective of these figures, I put these three bullet information. Yeah, dissolution and deposition of targeted metal is clearly the reaction of anode cathode. To push the production rate means that to push the dissolution process further or higher, and to push the deposition process higher, of course, increasing current density should be the solution. But then there are some concerns of increasing current density. If we increase the current density, then the total current that will flow into the electrolyte will be very, very high. Then this IR drop will be very problematic. So, and other area is also anode passivation. So if we increase the current density, what if we have anode passivation? What if the anode won't be dissolved? Because there is this gold in silver electrorefining, it cannot be dissolved. It doesn't really affect if we increase the current density because the material is not dissolving. And the last thing is that if we put high current density, then for the dissolvable contaminants, it will dissolve rapidly into electrolyte. Then there will be electrolyte contamination. So a lot of things needs to be considered for improving an electrorefining process. I don't want to highlight all of that problem, the increase of SEC, increase of the contamination, and so on. It can be found in my dissertation. But then I will highlight the anode passivation since we discussed about gold and silver. So if we have gold in silver anodes, the correlation of current density to potential will look like this. This is the cathodic side. So once we go to anodic side, boom, silver starts to dissolve. But then at some point, after the critical point, it gets passivated. It drops rapidly, like nothing dissolved there. So this is called the passivation region. And this is a region that we don't want to operate in. We want to operate either in the active region or the transpassive region. So after active, passive, and then transpassive. And increasing current density or increasing potential, it doesn't really result in increasing current density as much as we want, because as we can see here, once we increase potential here, it will increase a lot. But then after certain points, if we increase the potential, it will not increase as much as we want. So there is this optimum point here where another increase of potential will not affect that much. So in this study, I made this several several fabricated anodes. I made this with Dr. Imam Santoso. So we put silver and gold, and then we smelt it in the furnace, and then we make these buttons of anode, and I measured it in different sets of electrolyte conditions. So the result is like this. So when I calculate the critical point with the optimum point, so I should have higher, well, to have the best process, I should have higher optimum point rather than critical point, right? Because why should I put more potential if I don't get any higher point here? So it doesn't make any sense. So for example, for me, it doesn't make any sense if we operate like here, because it has higher potential than here, but then it doesn't really resulted in the higher current density. So I really want to have optimum point that goes higher than critical point. So how to investigate that? I play with percentage of anode in cathode, the acid content, and also the different temperature and silver content. So this is what happened. So the light shaded area is the optimum. It should be always on top. It should be. And the dark shaded area is the critical point. This is the unwanted we don't want this to be crossing this thing on the optimum point. So as we can see here, at this certain condition, yes, it's normal. So this is good. But after I altered the condition of electrolyte in arbitrary concentration or temperature, I didn't put the temperature here. So it seems at certain different condition, the critical point is crossing the optimum point. So this is the part that we don't want to operate in. For example, if we operate at 10 grams per liter of nitric acid here, note we already reached the limit. So if we put this as constant, and if we have more gold content in anode, then it's totally no. Totally no. It's not so efficient process. So if we have, like, for example, if we have a high, for example, 14 grams per liter, 14% of gold here, then we need to operate at lower acid concentrations and at lower current density. So this is logarithmic value. So so if we have in this B chart in particular, for example, if we have 10% of gold in the silver anode, we cannot really reach 1000 amps of operating condition or current density, because the logarithmic current density value that correlated is like 2.4 to 2.6. So 1000 is like we need to have 3 value of logarithmic current density. So this is what I did for my gold effect modeling to silver electrorefining. So I found that the gold needs to be limited. It's no discussion. It needs to be limited. And then also the concentration of nitric acid also needs to be lower. And then when we cannot really deal with the gold content and cannot really deal with the nitric acid, because why should we change the nitric acid concentrations like every time we get different kind of materials? So if a plant operates at a constant concentration or constant quality of electrolyte, then they will need to adjust the applied current density. So that's the bargaining of these 3 parameters here. And as conclusion from my study in Alto, and I how to say, it's my privilege to do this research in Alto University. I put into perspective of my findings and Maliaric paper. Of course, I said it too many times that this paper is like very how to say, motivating, and then the rest of it as conventional silver electrorefining. So to put into account, this is a mezzo autotech processing, the high current density of mezzo autotech, and then this is my doctoral dissertation. So these are the findings that I got. Yes, I agree to Maliaric that high current density can be applied with no problem at all in silver electrorefining. Yes, it can be applied. But then I also agreed the limitation of silver concentrations and also the limitation of temperature. I agree that the temperature is like needs to be lower than 50, so 35 to 45 is like the optimum point. But then I put into emphasize that this copper content in the electrolyte, it's actually not so detrimental to the process. I mean, if we have this high even though if we have like this high copper content in the electrolyte, it will not deposit it onto the cathode. I have one publication that proves that there is no copper deposition on cathode, while in Maliaric is not mentioned in the paper. And for cell voltage, in previous paper, it's like mentioned only less than 5 volts. In conventional electrorefining, it has a lower cell voltage, of course, because they operate at lower current. So it's quite logical. But then in my finding from empirical model, it's like this. From validation that I did, from validation model is like this, and from industrial measurements, I conducted this industrial measurements in 3 different industries. One in Hamburg, one in Nikkelverk, Norway. One in Harjavalta, Finland, and one in Jakarta, Indonesia. So I conducted this industrial validation in 3 different silver electrorefining facilities from Germany, Finland to Indonesia facilities. So it's a real value. And the current efficiency, for me, it's I had some difficulties in measuring current efficiency at that time. So I took the number that provided by Maliarik here, and then calculate further the impact of these parameters to the output of the process. So basically, I'm not really inventing something new. I'm how to say, put more agreement to, yes, silver electrorefining can be processed in high current density without any sort of problem. Even though if we have like high copper, high gold, high something, it's like, yes, we can tweak that process into for better production or productivity. And my dissertation has been, how to say, there were several companies also considering on optimizing their process based on this publication that we did in Alto. So one is in Mexico and one is in Asia and Oceania. I cannot really say in the company name. So I have this agreement with them. So yeah, so we have this finding, and which is useful for the industries. And yeah, thank you. That's all for me. And please, if you have any question and I can answer it, then it will be my pleasure. Thank you.
Very nice presentation, Mas Arif. In here I call Mas Arif because I don't know, I call Pak Zul or Pak, but here I call Mas Arif because we are very good friend in here, and
Yeah.
he's very good friend of mine. And starting when we are in bachelor degree, when he did his bachelor thesis in mineral processing lab, I joined with
Yeah.
him, accompany him when doing experiment. At that time, Mas Arif with her brother. Okay, guys, now please ask questions. I give you chocolate for the best questions. I already give chocolate, Pfizer chocolate to 100 gram to done. So any question will be appreciated with chocolate. So please ask
Yes, please.
question. Okay, this is very limited skill, or in Indonesia only limited maybe people who know this. So please ask, guys. And in the future, when you have
Oh,
hydrometallurgical process, it usually will be followed by electrowinning and electrorefining. So this is kind of one package. After you do leaching, you have to deposit the metal to electrode, and this is very good.
I think we have one question or even more. Farhan has raised his hands.
Okay. Yes, Farhan. I know Farhan. He worked in Antam
Yes.
in Pulau Gadung. He's doing a lot
Yes.
of work with electrorefining. Please, Farhan. I know you
Yeah.
have a lot of problem in there, and you want to optimize, and you ask me to help you.
Yeah.
But no, I bring the expert. Please show your
Okay.
face.
Thank you, Mas Imam, for the opportunities. First, sorry, I can turn on my video. Thank you, Pak Arif, for your presentation and explanation. Yeah, it's super detailed and informative for me. I want to ask about gold processing. We use electrorefining, the electrolyte from electrorefining use in Antam Logam Mulia, UBPP Logam Mulia, we use aqua regia instead of nitrate acid. Why? My question is, what's what is the effect of using aqua regia compared to nitrate acid? Based on your presentation, why Antam Logam Mulia use aqua regia than nitric acid for the electrolyte on gold electrorefining?
Yeah, for gold electrorefining, we should use aqua regia. We should use aqua regia. Nitric acid is for the silver electrorefining. Sorry if I miss saying or something like that. So yeah, so for gold, basically the role of electrolyte is like it needs to it needs to have the ability to dissolve the metals, and also it needs to have the conductivity. So
Hmm.
nitric acid cannot really
Yes.
dissolve gold, even though
Yes.
for high concentration it cannot dissolve gold. Gold needs a complexing agent, so that's why
Yes.
in wall wheel cell we use aqua regia. But for silver electrorefining we use a silver nitrate electrolyte, which is like and also a little bit or low amount of free nitric acid there. So we can check it from my slide if I can show it once more. I have these two tables of silver electrorefining and gold electrorefining process. Wait a second. New share. All right.
Arif pause screen share. You can share.
Okay, I will try. So have you guys seen the slide already?
Yes. Yes.
Yeah. So here, here we have this gold refining process. So yeah, in gold refining process, it use aqua regia, and then the free acid that shown there is like free HCl. So it has this very high concentrations of aqua regia of free acid there. But then for silver electrorefining, I will put this from my dissertation. Yeah. So for silver electrorefining, it has this nitric acid concentration.
Nitrate.
So
Yes.
yeah. So no
Okay.
hydrochloric acid concentration there. And the amount is like 2, 5, 10, not in hundreds, not in tens even. It's just like a very low single digit concentration. So this is the main difference of the two process. So basically, if you want to optimize your silver electrorefining process in Pulau Gadung, just use this from my dissertation. So this
Yes.
Yes.
electrolyte
Recipe for
parameter.
Pak Arif. Yeah. Yes.
Thank you,
Pak
Yeah,
Arif
Arif.
give you recipes.
Yeah,
Farhan.
currently
Yeah.
in Antam Logam Mulia Pulau Gadung, we use aqua regia for gold electrorefining, and we use nitric acid
Mhm.
for silver refining. So I think it's optimum, I guess, for today
Yeah.
best practice in Antam Logam Mulia. Thank you, Pak Arif, for your answer, and Mas Imam for the opportunity of giving a
Yeah.
question.
And one more yeah. And one more information for Mas Farhan. I will not say the value of electrolyte in Logam Mulia. I have the data, but just focus on this electrolyte concentration because one of the parameters I think you have rather high there in the process. So which can be a little bit how to say have negative effect on the process. So that can also can be one thing to optimize.
Yes, thank
All
you,
right,
Pak Arif.
thank you.
Okay, Farhan.
Yes.
Understood?
Okay, thank you,
So
Mas Imam.
basically, you have to something that can dissolve because it is ion. And after that, the ion need to move. It means conductivity. So So we have to get the chemical that has kind of properties. Okay, thank you,
Yes.
Farham. I think you got another chocolate. I still remember you. You have to come to Bandung, take the chocolate because it will melted if sent by courier. Okay,
What
next
about
question, please.
my yeah, my colleagues from Alto, Diana, you are there, and I can see some
Yes,
of my
I'm
colleagues from
here.
Alto, Diana, Sugam. How are you?
Yes.
Uh, I'm good. I miss you. We miss you in the office.
All right, yeah, nice, nice. Yeah, please, guys, if you have any further questions, I can answer it. If I will answer it if I can.
Okay, guys.
Right.
We still have time.
We still have time. Yeah.
Don't worry, we are not
So,
biting you.
yeah. So this precious metal refinery is how to say it's a competitive metallurgical business. I would say.
Yeah.
If we take a look into this slide, the amount of TCRC per year is much more competitive. Like people go more efficient through time. So and how to say so a precious metal refinery in Pulau Gadung, it can also be a competitor for a precious metal refinery in Finland or in other part of countries. For example, it's rather similar with the copper concentrate market. So copper concentrate produced by Freeport in Indonesia, it can be sent to Gresik, it can be sent to Spain, or it can be sent to any part of the world, depend on the competitiveness of the TCRC and the cost impact of that smelter. So yeah, having a very efficient precious metal refinery in nowadays is a must. Is a must.
Okay. Mas Arif,
Unless
maybe I have one
yeah, unless
question because
yeah,
okay, sorry.
yeah, for
Okay,
sure,
because
man.
now
Silakan.
currently I am helping Antam, and there are some problem that
Hmm.
some product uh, they not dissolve because they cast from the bullion, they cast the bar to put in the cell, and
Hmm.
after that
Hmm.
the it's not homogeneously dissolved, and sometimes it is
Hmm.
cut in some place and it is dropped. And what do you
Hmm.
think it caused that problem? It's from the defect during casting, the electrode is not very well, or what do you think?
Yeah. Yeah. So the geometrical defect can also be a problem. I mean, if a not smooth surface is produced there, then it can also affect the current density distribution on the surface. And
Okay.
the second one is that if this is the case in silver electrorefining, for example, this is the case, because I cannot imagine that it will happen on gold electrorefining, because gold anode is having quite high gold content, 95% up. But for silver electrorefining, this particular problem can happen, because
Yes, it is in
if there
silver.
is this
Yes.
gold, the, yeah, I can imagine, because if you have like very high gold content in silver anodes, then the gold will be passivates, and then
Yeah.
uh, some other active surfaces that has this exposed silver there, it will have like very intensify energy, electrical energy, I would say. So the current density in those active surface will be very high.
Yes.
It-
Yes.
yeah, and then the current density that
Dissolve.
goes there
Yeah.
is not, yeah, it will dissolve rapidly. So the homogeneous
Exactly.
dissolution,
Exactly. Yeah. Mm.
yeah. So uh, the solution is like, for me, is to have to categorize the type of input material that you have. I mean, this uh, this much amount of gold, for example, low, medium to high gold content of silver anodes, and then put them into the same cell, how to say, the same cell treatment, or what is in English, like, yeah, the same row. Because if you put, for example, low and high gold content, like this is low, this is high, this is low, this is high, then the current density is like really, distribution is really
Yeah.
in a mess there.
Not homogeneous,
but if you
and
have,
that's why the dissolution also not homogeneous, and then it's cut at
yeah,
some point at which it is have very high rate of dissolution. Do you agree with me, Mas?
yeah. So
Yes.
maybe better to have like high gold, silver
Mm.
electrorefining in one place, and low in one place, and medium in one place. So that's also
Yeah.
option. But a lot of things can be considered there.
I forgot
I
to
saw.
mention here also coming Dr.
Mm,
Taufik, Pak Taufik.
hmm, yeah, Pak Taufik ada
Pak Taufik
pertanyaan.
is the college of Pak Arif, guys.
No, I don't have question. It's a very nice presentation. I'm learning from a lot from Dr. Arif. Thank you.
Yes.
Yeah, Dr. Taufik is my close friend during bachelor degree. He helps me a lot on surviving in Bandung. So yeah, thank you very much, Pak Taufik. I saw that
Okay, guys. Yes.
Ma'am, I saw Mas Raden was raising his hand. Or maybe he still have some
Okay, Mas
question.
Raden. Mangga, Mas Raden.
Okay, thank you, Mas Imam, for the opportunity. I want to ask a question about jewelry gold, or maybe gold from our handphone or electrical devices that needs gold. How can we process that into new product? Is it the process the same with has been taught before? Because I'm afraid the content of gold is really high in that material. Thank you, Mas Arif.
Yeah. Yeah, usually yeah, that's as also mentioned, that gold bearing material can be also jabil scrap. Yeah, in my old days in Antam, in Pulau Gadung, yeah, we process the jewelry that has this high content of gold directly to gold refining, because it has very high gold content there. So, but in jewelry, it's it's rather easy, I would say, because as you mentioned, it has high gold content, then it will go directly to the gold processing route. So it's similar with any other gold bearing materials that we have here. And the most tricky thing to be processed here, among these four types of materials that usually a PMR receive, is the anode slime, or sludge or precipitates, the last two. Because un, unlike the bullion or jewelry scrap, they already in the fine metal form. The anode slime and sludge, they still in oxides, and sometimes sulfate forms, and this kind of thing. So it has a lot of impurities, and which can be affecting the recovery of the process. For example, in anode slime processing, if the anode slime contain high amount of lead, or high amount of copper, not to mention the bismuth, the arsenic, and those nasty stuff, it can affect the recovery quite badly. Quite badly. I mean, it's not even economic to process a certain type of slime. But for jewelry scrap, I don't think it's a problem.
Impurity is the matter, ya, Mas. As pure as possible, it's better to process. Yes.
Yeah.
Okay, guys, any more questions?
Do we have participant
Okay,
from
let's check.
China, Imam?
From where? From China?
From China.
Yes,
Do we have any
some.
attendee from China here? Oh, nice.
Yes.
Nice to have you guys here.
Yeah. Okay, guys. If there's no more question, let's give applause to Pak Arif. And thank you very much for nice presentation, Mas Arif, and sharing